All right, today we're going to pull back the curtain and look at the secret life of a process. We're going to tell the hidden story of what actually happens inside your computer, in those few moments right after you double-click an icon. So let's dive in.
So you click on an app, right? And poof, it just appears on your screen. It feels like magic, but of course, it's not. It's actually the beginning of a whole journey for something called a process. And trust me, understanding this journey is the key to figuring out how your computer can possibly juggle so many things at once.
Okay, so our story really starts with this big transformation. We're talking about going from a simple, kind of boring file just sitting on your hard drive to something that's alive, a living, breathing task that your computer has to actively manage.
Now, the difference here is super simple, but it's absolutely crucial. Think of it like this. A program is just a recipe sitting in a cookbook. It's passive, right? It's just a set of instructions. A process, though, that's the chef in the kitchen actually cooking. They're using the recipe, mixing the ingredients, turning on the heat, and making something real happen. A process is a program in action.
And get this, it's not always a one-to-one thing. You might have one Chrome application installed, but if you open up a bunch of windows or tabs, your computer is actually juggling multiple separate processes. This is exactly why sometimes one crazy tab can freeze up, but you can just close that single tab without crashing your whole browser. It's because they're all different chefs, all working from the same recipe book.
All right, next up in the story is the process lifecycle itself. And yeah, just like pretty much any living thing, a process goes through these really distinct phases, from the moment it's born to the moment its job is done. So first, it starts as new. This is while the operating system is getting everything ready for it. Then it moves into the ready state. It's basically in line with a bunch of other processes, just waiting for its turn on the CPU. Running, that's its moment in the spotlight. That's when the CPU is actively crunching through its instructions. But if it needs something, say to grab a file from your hard drive, it goes into a waiting state. It's paused. And then finally, once it's all finished, it becomes terminated. Job done.
Here's a perfect example. As you're scrolling down a web page, your browser process is in the running state. But the second you hit download on some huge file, it might switch over to waiting. It's waiting for that data to come in from the internet. And while it waits, the CPU is freed up to go do other things. Pretty efficient, right? Okay, so if you've got all these processes hanging out in different states, how on earth does your computer keep track of it all without, dropping the ball? Well, this is where your operating system steps in and basically becomes a master juggler.
And to manage this whole circus, the operating system gives every single process something called a process control block, or PCB for short. Honestly, the best way to think about a PCB is like an official ID card for the process. It holds absolutely everything the OS needs to know about that specific task.
And this isn't just some flimsy ID card, it is incredibly detailed. It keeps track of the process's current state. Is it running? Is it waiting? It knows the exact next instruction it's supposed to execute. It stores all the crucial data in things called registers and holds all of its memory details and scheduling info. It's literally the process's entire world, all packed into one tidy little data structure. So this brings us to what is really the central magic trick of modern computing. How can your computer run your music, your web browser, and your word processor all at the same time? The secret is, it isn't. It's not doing them all at once. The trick is switching between them so incredibly fast that it just looks like it is. And this super fast switch has a name. It's called a context switch. This is the fundamental trick, the core mechanism that makes multitasking possible on a single CPU core.
So here's how it works. When it's time to switch tasks, the operating system takes a perfect snapshot of everything Process A is currently doing. It saves its entire context, all that info from its PCB, that ID card we were just talking about. Then, in the blink of an eye, it loads the saved snapshot for Process B. And just like that, Process B picks up exactly where it left off, with no idea it was ever paused. And this whole dance happens hundreds, maybe even thousands of times every single second. It's mind-bogglingly fast. But there's a catch. This amazing juggling act isn't free. The time it takes to do the switch, that's pure overhead. It's wasted time. During that tiny fraction of a second, your computer isn't actually running your browser or playing your music, it's just doing paperwork, basically. The whole goal is just to make that switch so blindingly fast that you never even notice it's happening. Okay, so we've got a handle on what processes are and how they're managed. But where do they all come from? They're not all created when you first boot up your computer. Turns out, new processes are actually born from existing ones, which creates this kind of cool family tree structure.
So you'll have a parent process that creates a child process, maybe to handle some specific task. And then that child can go on to have its own children, and so on, forming this whole hierarchy. And every last one of them gets its own unique ID number, which we call a PID, or process ID.
On systems like Linux or Mac OS, this is done with a couple of really famous system calls. First, there's fork. This is basically the command for a process to say, clone yourself. It makes an exact duplicate. Then, the new child process will often use exec. That's its way of saying, okay, now I'm going to transform into something totally new. It wipes itself clean and loads a new program. So it's this classic two-step dance, clone and then transform.
All right, for our final chapter, let's talk about how these processes can actually work together. Because, let's be real, sometimes one single process just isn't enough to get a really complex job done. They need to cooperate. And there are some really good reasons for them to team up. For one, they might need to share information. Or you could take a massive calculation and split it up among a bunch of processes to speed things way up. It also just makes it easier to build big, complicated apps from smaller, more manageable pieces.
Now, this kind of cooperation requires something we call Interprocess Communication, or IPC. And there are basically two main ways to do it. The first is shared memory, where processes get access to the same chunk of memory. It's just like two chefs sharing the exact same pantry. The other way is message passing, where they stay in their own separate kitchens and just send written notes back and forth to coordinate.
You know, a classic example of this in action is something called the producer-consumer problem. Just imagine one process is the producer. It's downloading video frames from the internet. And another process is the consumer. Its job is to display those frames on your screen. They have to talk to each other to make sure the producer doesn't get way too far ahead of the consumer, or you end up with dropped frames.
So how does this actually happen out in the real world, especially when you're talking about computers on a network? Well, a lot of the time it's through something called a socket. A socket is really just an endpoint for communication. I love this analogy. Think of it like a specific, numbered dock at a huge, busy port. Two ships, or in our case, two processes, know that they can meet at dock 24 to exchange their cargo.
So there you have it. From that one simple click to this incredibly complex web of cooperating, communicating tasks, there's a whole secret life unfolding inside your machine every single second. So the next time you see that little loading wheel spin, don't just get frustrated. Ask yourself, what's really going on here? Is that process in the waiting state, maybe for something from the network, or is it just stuck in the ready queue, patiently waiting for its turn? Because now, you know the real story.